Page break. Today is September 8, 2025, Monday. So let's start with how physics is put together, how physics is put together, or the building blocks of physics. How do we start in physics? Okay, so there are only three different concepts in physics, which is the starting point. Okay, let's put here the starting point, physics, the starting point, or the starting point of physics. Starting point of physics. Okay, there are three basic ideas in physics that we start, where we start from, and first one is the basic quantities. Okay, in the case of basic quantities, you already know about them. You just don't know. You just don't know them by this name, okay? Don't know them by this name. And then the other two are, I would say, should be new for you. Primary definitions and the laws of physics. Okay. And let's start with the basic quantities. Let's start with the basic quantities here. Are the core quantities that are used in physics. The core quantities are used in physics. Everything else, every other quantity and or definition will be a combination of these basic quantities and also the primary definition, okay, like that. So every other quantity that we introduce in physics is going to be a combination of those two right in here. The basic quantities and the primary definitions. These core quantities combined with the primary definition, the laws of physics, allow us to formulate most of what we know in physics. Okay, it is because of this concept that we can, it is because of these three concepts that we can predict the orbit of satellites, build the internal combustion, an internal combustion engine, build your cell phone, TV, etc. It starts right in here. Every other quantity in our definitions will be a combination of these three basic quantities, and will be a combination of these three will be a combination of the, here you go, basic quantities and also the primary definitions. So let's start. Let's see what those basic quantities are all about, okay? So here you go. I like to display that as a table. You should be aware already of the basic quantities. Is something that we learned since we are a little kid. So there's nothing much about a secret about the basic quantities because we learn them while we grow up. We take them for granted. But when, but think about the caveman, right? That the caveman that was start to develop these ideas. At that time, those quantities were not obvious to them. Nowadays, it's obvious because we grow up with them. People tell them, and we just learn becomes a second nature. There are a total of seven basic quantities, but we are going to start with only three of them. I don't want to overwhelm you. Okay, here you go. Three basic quantities. Later on, we're going to talk about the other four. What happened here? Length is one of them. And the length is measured in the International System of Units. It's measured in meters. Time is another one. And mass is another one. So those are the three that we're going to concentrate for now. For most of this course, we're going to concentrate on those three. But like I said, there are seven. Okay. Length, time, and mass. Simple enough? Okay. In the case of the primary definitions, we have two others. And we say that they are vectors too, okay? Here go, laws of physics. There are two. We're going to talk about vectors later on. So let's not worry about vectors and scalars for now, okay? I'm going to just stay as a reference for you, future reference, just to distinguish the primary definitions from the basic quantities. The basic quantities are scalars, and the primary definitions are vectors. But we're going to talk about vectors and scalars later on. Okay, so here you go. What are the primary definitions? The primary definitions are the position of an object, which is also measured in terms of the length, but it's not length, okay? Length is a scalar quantity. Position is measured in terms of length, but the position is a vectorial quantity. And one more thing, this position can be negative or positive. A length cannot be positive or negative. Neither time, okay, nor mass. There's no such a thing as a negative mass or a negative time or a negative length. Position. And then we have this other concept that has been around since antiquity, which is called force. A force is a push or a pull. Its unit is going to be what we call the Newton. The Newton which is a combination of kilogram, meter, and second. Kilogram, meter per second square. And this combination and this unit comes from one of the laws of physics. One of the laws of physics that we are not going to introduce yet. We're going to introduce them later on. Okay, here you go, laws of physics. We're going to introduce them later on. Okay, so I like to say that at the beginning of even before the beginning of civilization, right? I would say caveman and cavewoman at the beginning felt the need to make sense of this world. In order to do that, right? We'll do that. We had to invent some abstract concepts that were then implemented in practice. And those abstract concepts as length, time, mass, position, and force is a concept that came later on. These abstract concepts today we call basic quantities of physics. They are the length, time, and mass, the three most important ones. Later on, other ideas were added, other quantities were added to this list. 4 more. They are so important today. They are so important that today we take them for granted. We grow up with those things. We learn, we just absorb from everybody around us. Right now, they're just second nature to us, but it hasn't been second nature forever. Okay, they came about to be long time ago. Later on, okay, we came with other ideas. For instance, the idea of hot and cold. For instance, the idea of hot and cold, and the idea of quantity of a substance, and that is measured in terms of the mole, right? And electric charge, the idea of electric charge as well, which is measured in terms of the Coulomb. Those are the other 4. And finally, luminous intensity, which is measured in terms of the candela. Candela comes from candle, the word candle. And then I'm going to add them here. Okay, those are the other, let's see, 1, 2, 3, 4. 4 more basic quantities that we're not going to explore right now. We're going to explore later on in the course. We start with those 3 most important ones. Oops. Okay. Here, 1, 2, 3, 4, 5, 6, 7. 7 basic quantities. For the sake of this course, it's okay to believe that all these 7 basic quantities are independent of each other. This is not 100% correct, because 120 years ago, someone that you have heard before, right? His name was Albert Einstein. He proved that those basic quantities are not independent of each other. They are dependent on other things. And that's something that we are going to learn in physics 7. Okay, so but for the sake of this course, it's okay to believe that. Let's see, someone sent me a message here. Oh, you're not able to hear me? Okay, thank you. Let's see here. Can you hear me? There's a student that cannot hear me. Everybody can hear me, right? Okay, good. Thank you. Okay, good. So it looks like the problem is on the student side. Okay, a little bit more about the primary definitions, right? So I covered the basic quantities long enough, and the primary definitions, just position and force. And we're going to use a lot this idea of position at the beginning, and later on we're going to use a lot this idea of force as well. Okay, the difference between basic quantities and the primary definition relies on their mathematical nature. One is a scalar. One is a scalar quantity, if you have already seen that in math, right? And the other is a vectorial quantity. What does it mean? You know, vectorial quantities have a direction. Scalars do not have a direction. No direction associated to a scalar. That's the important difference between scalar quantities and vectorial quantities. Here is, let's say, a magnitude, okay? Magnitude, but no direction. A vectorial quantity has a magnitude and direction. A scalar quantity is always positive. No direction is always positive. Always positive. Okay? These vectorial quantities can be either positive or negative. Very important difference between those two concepts. In math, we have this important duality of scalar quantities versus vectorial quantity. Scalar quantities can be measured only in terms, are measured only in terms of its intensity, are measured in terms of their intensity and direction. And depending on the direction, we say that the quantity has a negative value, depending on the direction, right? We say that the vector has a negative value. Examples. Examples of scalar quantities. Examples of the scalar quantities. Regular numbers. 1, 2, 3, 4, etc. It can be 5.2 as well. Doesn't have to be. Okay, are scalar quantities. The positive numbers, right? The positive numbers are scalar quantities. And let's see, example of vectorial quantity. Example of a vectorial quantity. Let's say, I'm going to give you an example of vectorial quantity. The position of an object. It can be stated, for instance, that the position of a given object is, let's say, 3 kilometers south of downtown LA, okay? Downtown LA, for instance. Or 5 kilometers north of downtown LA. Here we are specifying the magnitude of this position, and we are also specifying this direction with respect to a given reference, which is downtown LA. Usually the south direction is considered to be the negative value, right? Usually the south direction is considered to be the negative value. Such like that in the latitudes of places. Any city below the equator has a negative latitude. Any city above the equator of the Earth has a positive latitude. Okay? Here we have units. We have units of physics as well, right? That is how we quantify a basic quantity. That's how. So we go in meter. In the case of lengths, the commonly used unit accepted internationally, right? Because the commonly used unit accepted internationally is the main SI international system of units. That's what SI stands for. It's their acronym. Is the French acronym. Let's put it this way: the French acronym for international system of units is the meter. In the case of time, the SI unit is the seconds, abbreviated by S. In the case of length, the commonly used unit is the meter. Let me here write that. Unit is the meter. Let's put in the main. Let's see. Here should be in, okay? In the main system of international units. So we gotta put it back. This one there is the meter, abbreviated as M. Gonna put it between quotes. In the case of time, the SI unit is the seconds. In the case of mass, and what is mass? Mass is a measure of the quantity of matter in a given object. That's what would be a good definition of mass. Is the kilogram or kg. The position, I'm just repeating what I said before, right? The position of an object is always specified in terms of a length plus the relative position of this object, the relative location of this object with respect to a given origin. Okay? In this case that I used in the example that I gave above, for instance, downtown LA. Suppose that we can specify a point in downtown LA that can be used as an origin. This position is represented by an arrow. Okay. Okay. In the case of a Cartesian system of units, okay, the position of an object is measured with respect to the origin of the Cartesian axis, which is the intersection of the x and y axis. This point, we denote the origin of the Cartesian system, I'm going to start showing some illustrations. It's always good to illustrate, come up with illustrations, right? So you can have a pictorial idea of what you're talking about. Here you go. In the case of a Cartesian coordinate system, you already know that we have a x-axis, right? The horizontal axis, which we denote as being the x-axis. And this x-axis must have a unit. And we must also, whenever we are dealing with any coordinate system, doesn't have to be a Cartesian coordinate system. We must always specify our origin for this coordinate system. Here you go. In this case, we set the origin anywhere along this axis, and this origin is denoted by the number 0. 0 meters. 0 meters from the origin. Okay. Then we come up with the different positions, right? Let's say here is 1 meter, 2 meters, 3 meters, 4 meters, just like a ruler. 3 meters, 4 meters, 5 meters from the origin. And to the left of the origin, we have the negative positions, -1, -2 meters, -3 meters, and so on. Example. I gave you the example of the object, let's say south or north of downtown LA. Now I'm going to give you an example of the position of an object with respect to this one-dimensional Cartesian coordinate system. This is a one-dimensional system, and that's how we start in physics, right? We deal with one-dimensional system first, and then we elaborate to 2 dimensions and 3 dimensions. In this specific case, here you go. We have this example. We have the position of this object, this blue object that I put here along the axis. The position is 5 meters. Because the position is a vector, the position of the object is a vector, we can also denote it as an arrow that goes from the origin to the point where the object is located. That's how vectors are denoted graphically. Okay. And to describe one-dimensional motion, for instance, we illustrate a particle along the x-axis. And that's what we're doing here. And let's say at time t equal to 0, the position of the particle is 5 meters from the origin. Let's say that. Okay. And then let's say, and this particle is moving along this axis, right? And let's say after a certain amount of time, the position of this particle changes, is 3 meters. Okay, it moved from 5 meters to 3 meters along this axis. Here in this case, let's see here. Oh yeah, here you go. If at t, I want, yeah, I want this guy here in the previous one. We don't need this one. Let's see. We don't need this one. This is slide here. This slide here is redundant, right? So here you go. Let's eliminate it. Okay, so that's the initial position of the object at initial position time equal 0 seconds. That's, let's say, the final position of an object at time t equal to 4 seconds. I'm using the idea, the idea of primary definition, the idea of a primary definition, which is the position, and the idea of one of the basic quantities, right? Instant of time. Instant of time. And in both cases, the position of the object can be denoted in terms of this red vector. And red vectors are denoted in terms of an arrow, okay? I'm gonna put this vector, here you go. Here is the initial vector position. Going from the origin to the initial position of the object. And I'm gonna duplicate this slide. I don't need that, here you go. Initial position. And then I also have the final vectorial position, which is the vector that goes from the origin to the 3-meter position. Yeah. My mouse I'm having a problem with my mouse here. It looks like I gotta buy a new one. Here you go. Initial vector position, final vector position. And I can even call it, x naught. This initial vector position, call it x naught. The other vector position, I'm gonna call xf. Right? Is the name, don't forget, it's the name of the vector. Gosh, let me put it here. And I want to view the grid lines. I don't like the grid lines because it looks so ugly. Okay, 3 meters. That's gonna be my XF. For now, I'm not using the vectorial notation. Vectorial notation is gonna come later on. Okay. So let's, I'm going to document what I mentioned right here. Other examples of vectors in physics, right? Other examples of vectors in physics. And by definition, you already know that we have the position, the force. But then we have some other vectors that we can define as well. And that's what I'll call a secondary definition. And another vector that we have in physics is the displacement vector, which is the final position minus the initial position. Let's put minus there. Yeah. And then we have this other definition, the tertiary definition. Okay, notice that this secondary definition here is a relation between two different positions. But for this tertiary position definition, which called velocity, is going to be a combination of a vector and a scalar. Displacement divided by amount of time. Final position minus initial position. So those are two important examples of vectors, and there are other vectors. Okay? There are other vectors that we are going to study extensively. Acceleration vector. We have the linear momentum vector. We have the angular momentum vector, and so on. The next one that we are going to study is this one here. For the sake of this first few meetings, you have to understand those three important vectors. Four important vectors, right? The position first. We're going to deal with force later on. The vector displacement, the vector velocity, and the vector acceleration. Those, for the sake of for the sake of the next few meetings, at the beginning of the meeting, you must know and understand, right? And understand the following vectors. 1, vector position. 2, vector displacement. Vector velocity and the vector acceleration. And the way I like to display those ideas is by justifying them below the other, just to emphasize the fact that this vector depends on this one, that this vector depends on this one as well, and this vector depends on this other vector plus something else, okay? Plus something else. Those are the 4 important vectors that you must have a clear idea for the next few meetings. And then we're going to get into more vectors than that. So how do we, let's start with the vector displacement, right? You already know how we denote a vector. A vector is denoted by an arrow. Must be that my mouse is too sensitive. Okay, so here you go. Vector, initial vector position, final vector position. And then we can denote the displacement vector as a vector going from the initial position to the final position. See that? Okay. Going from the initial position to the final position. And that's the very definition of displacement. Is the final position minus the initial position, like I defined before, right? So I'm going to write that down in terms of mathematical ways, in a mathematical fashion. Vector displacement. Vector displacement. I'm going to insert an equation right here. And I denote the vector displacement by a delta x. Okay? X for position, delta for difference in position. The symbol delta is commonly used to denote difference. Okay, and here you go. Final position minus initial position. Example, numeric example. Numeric example. Consult F initial position. Let's see. The one that I showed there in the illustration, right? Initial position equal to what? Was that 4 meters? Let's go back there. No, it's just 5 meters. 5 meters. Don't forget, I'm going to emphasize that at 4 meters in the positive direction. and the final position, which I also call x1, right? The final position is 3 meters. Okay, I'm gonna xf equal to x1. X1 is final position plus 3 meters. Plus 3 meters. Now we calculate the displacement just like that's one possible problem that you can find in the exam, right? Calculate the displacement of a given object. Here you go, final position plus 3 minus initial position. And I'm going to put that between parentheses, like that. Minus plus 4 meters. And then you do the mass. This is a straightforward type of mass. It's going to be 3 meters minus 5 meters. And then here you go. Your displacement, which is a vector, is can be a negative number, minus 2 meters. What does it mean, minus 2 meters? It moved 2 meters to the left. And again, that's how we denote the displacement vector here. In addition to vector, okay? I'm talking just about the vectors, right? The vector displacement also have a scalar counterpart, okay? Which is called distance covered, okay? Distance covered. And we denote by the letter D. Distance covered. Okay. The odometer of your car, for instance, documents the distance traveled by your car. It's a scalar quantity. What you see in the odometer of your car, in other words, what you see in the odometer of your car is a scalar quantity. It doesn't tell you the direction that you moved, right? It just tell you the distance that you covered. Just tell you the distance that you covered. Okay, so so now we have length, right? In addition to length, we also have distance covered. Paragraph. I want everything in single spacing. Here you go. The distance covered depends on the length. And now we have position vector and displacement vector. The displacement vector depends on the position. The distance covered depends on the length. So we have something else, the velocity, right? Let's look at the velocity vector. Then it's, I'm going to put that between parentheses. Its scalar counterpart is the speed. Just like the speedometer of your car, okay? Just like the speedometer of your car. So What's the definition of the vector velocity? The definition of your vector velocity is a tertiary definition. You go V. V is let's put it this way. It's going to be delta x over. I'm gonna copy that. You know, divided by delta t. Okay. Is a combination of a vector and is a combination of a vector and of a scalar, right? And this scalar is a basic quantity. So now we have that example that we saw before, right here. Here you go. Took 4 seconds for the particle to move from 5 meters to 3 meters. Okay? 5 seconds for the particle to move from 4 seconds for the particle to move from 5 meters to 3 meters. Looking at the example, in the note, in the illustration, right? We have delta x, that is minus 2 meters, yeah, and delta t, that is 4 seconds. Just regular algebra. Let's not forget, delta t stands for final instant of time. Let me do another step here. Let's see. I want to be consistent with the other one. Here you go. Like that. X final minus X initial. T final minus T initial. We already calculate delta X, right? Delta X was 3 minus 5, which is minus 2. And delta T is going to be 4 seconds minus 0 seconds. And now I'm going to simplify. By simplifying, I mean I'm going to get rid of the parentheses here. And I will get rid of the delta, the T naught. Then I'll further simplify that by moving the negative sign to the outside of the fraction. And I am going to simplify 2 is 4. And that, what we get for the final answer is going to be half meter per second. Meter per second, like that. Just like regular algebra. I gotta put this equal sign here. Minus half meters per second. Okay. Now going back here, let's see. We calculated. Okay. From the above example, right? Oops, it's not display. Let's see. This from the above example, the distance covered is plus 2 meters, right? The above example that we did right here. If delta x is minus 2 meters, the distance covered is going to be plus 2 meters. I'm gonna write that down here, d equal to plus 2 meters. And now we also have the scalar counterpart of velocity is the speed, right? Which is given by, is a similar equation, but it has a different meaning. The speed, I'm going to denote by the letter S, but don't mistake it by the second, right? Denote it by the letter S for speed. Instead of delta x, we're going to do at d. The speed is the distance covered divided by delta t. The distance covered is 2 meters. Remember, distance is a scalar, which is a positive number. And then we end up with the same numeric result, but a different sign. A different sign. Half meter per second. 1033. Okay. So let's see if we have here go. Let's see if we have something else here. Now, in this case, this is just another example, a different example than the previous one. Let's see. It's moving, the particle is moving back to its original position, right? Initially, it was at x naught equal to 5 meters. It moved to x1 3 meters, and then move it back to x final 5 meters. Okay. And we have t equal t1 is 4 seconds. Let me put another one here. T equal to t naught equal to 0 seconds. And now we are going to see clearly the distinction, the numeric distinction between distance traveled and displacement, okay? Going back to our illustration. We have the following. One, initially, the particle was at x not equal to 5 meters. Then it moved let's put it here, meter, at t naught equal to 0 seconds. Make sure it looks nice. Go up, supposed to be x naught. Then it moved to x naught, I'm gonna put x1 equal to 2 meters at, and then I'm gonna write it down, t1 equal to 4 seconds. It finally moved to it finally moves to x final equal to 5 meters at t1 equal to 6 seconds. Okay, here you go. 6 seconds. Another example, right? Another example. The question I'm going to ask you, what is the displacement between, here's supposed to be TF, between TF and T naught, oops, between TF and T naught, right? Now we're going to, what the displacement and the distance traveled between TF and T naught. Solution. Let's do the solution, then we go for a break, okay? Distance traveled now is going to be different because we added a second displacement, right? XF minus X naught. In this case, XF coincides with X naught, right? And now TF minus T naught is going to be 6 seconds minus 0. These ones cancel out the other one. And that's what's going to be the average velocity. We call it the average velocity, okay? I should have told you that. Let's see. Displacement vector, position vector, vector average velocity. Average velocity. That's a better definition. Average velocity. What is the displacement? Let's see. Let's see. What is 1? 1. The displacement vector. What is the displacement vector? 2. The distance traveled. 3. The average velocity vector. 4. The speed between TF and T naught. We want all those 4s, okay? The displacement vector, I skipped the displacement vector, right? But you already have it here. The displacement vector 1. Displacement. Delta X is delta X equal, okay, good. 5 meters minus 5 meters, 0, equal to 0. And this distance traveled, now distance traveled is going to be different, right? Distance traveled, okay? Distance traveled is going to be total distance traveled is going to be D1 plus D2. Remember, right? And just two different distances he traveled. He traveled, going back here. he traveled 2 meters to the left and 2 meters to the right. D1 plus D2 is not going to be 0. It's going to be 4 meters. Right? Distance traveled is always a positive number. So we go 2 meters plus 2 meters. So the distance traveled can be different from the displacement because of its very definition. And then we have average velocity vector, average velocity vector, which was the first one that we did, right? You got delta x over delta t, 0 meters per second. And now we have speed, average speed. Average speed, you go. S is going to be D divided by delta t. It's going to be 4 meters, right? Here is 6 seconds. Downstairs is 6 seconds. And let's see, 4 divided by 6 is going to be 2/3. 2/3 meters per second. Note, see that even though it's exactly the same displacements, right? Because we have different definitions, the average velocity ends up being different than the average speed. Just to emphasize, yes, it will be posted. They will be posted. The notes will be posted. They are always posted. You can also consult the notes from previous years. Okay, Melissa? You can also see the notes from 2024 posted there as well. I always post my notes from the previous semester, from the previous course that I taught. Okay? Okay, so let's take attendance. Right now, I'm required to keep attendance the first 2 weeks. So, and then we can go for our break. Attendance, this one right in here. Lab lecture. Today is the 8th. Okay, let's see. Sinoe? Is Sinoe there? Nope. Eric Alcala.
Here.
Thank you, Eric. Next is Edith Alexandrian.
Here.
Thank you. Next, Jawaria Ali. Jawaira. I can see Jawaira here in my list. Let's see. Let's see. I have two questions. One, is the lecture portion of the course mandatory, or can we watch the recorded lectures on our? Okay. Okay. So there is a student here who's asking, who's having problems with the homework. Anybody had any problems opening the homework that I posted in Wiley Plus? Let's take a look there. Okay, as I do attendance here, as I call attendance, I will ask you, okay? So Jawaira, let's see, Jawaira. I see Jawaira here. Let's see, but I cannot hear Jawaira. Jawaira.
President,
Oh,
hi, good morning.
okay, good morning. Thank you. Can you see the homework in Wiley Plus, Jawaira?
Yeah, I've got the course and I can see it in there.
Okay, were you able to open it too?
Yes, yes.
Yes, okay. Okay, so that's one of the students, okay? So let's see, Nestor Alvarado. Nestor there. I don't see Nestor here. Evelyn Ayala.
Here.
Okay, were you able to open the homework?
Yes.
Yes? Okay, thank you. Ben Bendoy.
Yeah, I'm here.
Were you able to open the homework, Ben?
Yes.
Okay, thank you. Melissa.
Hi, I'm here.
Were you able to open the homework, Melissa?
Yeah.
Okay, thank you. Miasia, Brad. Let's see. Miasia. I don't see Miasia here. Madeline Brock.
Here.
Okay, or you will be able to open the homework, Madeline?
Yes.
Okay, thank you. Cynthia Candelario.
Here.
Were you able to open the homework?
Yes, I was able to.
Okay, good. Okay, so Queen Castaneda.
Here.
Okay, thank you. Were you able to open the homework, Queen?
Yes.
Okay, thank you. Emily Serna.
Here.
Okay, were you able to open the homework, Emily?
Yeah, I was able to.
Okay, thank you. Cecilia Chavez.
Good morning, I'm here.
Okay, were you able to open the homework?
Yes, I just had a quick question. The due dates are gonna be December 16th for all the homeworks?
Yeah, that's right. So you have plenty of time to
Okay.
do the homework. Okay.
All right, thank you.
Isabella Cisnero. Let's see if Isabella is here.
Yeah, I'm here.
Okay, thank you. Were you able to open the homework, Isabella?
Yes, I was.
Okay, thank you. Jacob Contreras. I don't see Jacob here. Let's see. Okay. Delisha?
Yeah, I'm here.
Okay, so yeah, did you try to open the homework again, Delisha?
Yeah, I tried to open it again and it just buffers and then it says if you want to close the window, but there's no assignments or anything attached to it. I can see all of the assignments that you posted and all the due dates,
Really?
but when I click on it, it's not letting me, like nothing else pops up.
Yeah, check with Wiley Plus. They have how do you say that? They have someone to talk to you through it. Okay, let me check my own Wiley Plus here. Wiley Plus. They are usually very good at resolving those problems, right? Customer support, Wiley Plus customer support, and log in. I gotta accept it here first. Yeah, see, you can talk to customer support right here in this chat.
Okay.
Let's see, physics. It's taking some time. Okay, so here you go. Homework 1, right?
Yeah, mine doesn't launch
open
like that at all.
assignment. Open assignment. Yeah, let's see, question 1. Let's click here. Oh. Okay, I shouldn't see a newspaper ad for an apartment that has blah, 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 right? How many square meter of area are there? Okay. So that's the
Okay,
first
I
one.
will contact customer support then to see what's
Okay.
going on.
Okay, thank you.
Okay, thank you.
Let's continue here. Gabriela Edwards.
I'm here.
Thank you. Any problems with the homework, Gabriela?
No, I can open it.
Okay, good. Thank you. Angelica Franco.
I'm here.
Okay, thank you. Okay, I'm going to assume that nobody else has any problems with the homework. Okay, so Princess.
Hello, I'm here.
Okay, thank you. Carlo Gallardo.
Here.
Thank you. And Brandon Guerrero.
Yeah.
Thank you, Brandon. Arturo Lagunas. Arturo. Yeah, I don't see Arturo here. Jenny Maldonado.
Hello, I'm here.
Thank you. Isabel Medina. Hello, Isabel. I see Isabel here, but I don't hear from her.
Hi, Professor.
Okay.
Sorry.
Okay, thank you. Stephen Mikhail. Let's see if Stephen is here. No, I don't see Stephen. Yeah, Stephen. Kimberly Morales.
Present.
Okay. Thank you, Kimberly. Montserrat Morales.
Here.
Thank you, Montserrat. Erica Musa. Erica, let's see. I don't see Erica here. Corina Pais. Let's see if Corina is in my list. I don't see Corina in my list. Nope. Arwa Paris.
Yeah, I'm here.
Thank you. Catherine Perez. Catherine Perez. I don't see Catherine Perez here in my list. Nicolas Rivera. I see Nicholas here in my list. Are you there, Nicholas?
Yes, I'm here.
Okay, thank you. Elizabeth Saldana.
I am here.
Thank you, Elizabeth. Armand Taif.
Yeah, I'm here.
Thank you. Jania Tapia. Jania Tapia. I don't see Jania. Next. Juan Torres Arellano.
Here.
Thank you, Juan. Marian Ziaduin.
I'm here.
Thank you. Jason Sevillon.
I'm here.
Thank you. Sydney Hill.
Here.
Thank you. Okay, 32 students. 30 only. Okay, so it's 10:57 right now. Break. 10:57 a.m. Let's see, 12 a.m. Yeah, 11:12. So I see you in 15 minutes. Okay. Thank you. Stop sharing. I am back. See, we're recording, and let's start sharing the screen again. So let's see here. Let's go back here to the syllabus, right? We are writing here. Let's see. Okay, we met on Wednesday. We couldn't do the Excel graphs yet. And we couldn't do the lab group assignment either, right? So we're going to do that on Wednesday. On the motion. Okay, so let's see here. Yeah, okay, everything we're doing Monday. Well, Monday right here. Units dimensional analysis, 1D motion. Wednesday, we are going to do group assignments. Okay, let's see if it fits here. Group assignment. Assignment. Let's put this way, group assignment. And then I fix the rest. Sig figs, yeah. CL. And group assignment, Excel graph. Yeah, it looks like I'll have to leave two lines, okay? And okay, so can leave this way. Let's see. Hello, okay. Course section ID. Okay, okay. The 6-digit course section ID is in the syllabus. Let me show you the syllabus again. It's also in that flyer that I posted in Canvas. Here you go. B00230. Okay, Ben? I'm gonna send you a 6-digit course ID. Yes, here you go. Okay. Now, units in physics and dimensional analysis. Okay, units in physics. You already know that the main units of physics, are meter, second, and kilogram. There are 4 more, but we're not going to touch them yet. Okay. And you also saw, so here you go. When you're talking about units, we denote the unit of a given quantity by a square bracket, okay? So let's say here, if I want to know, for instance, the unit, okay, the unit of x, right? X is position. The unit of x is going to be the meter. And like I said, we usually denote the unit of a given quantity with a square bracket around the quantity. In the case of delta x, for instance, delta x, right? Remember that delta x, we go to the definition of delta x. The definition of delta x is what? Is x final minus x initial, okay? And in order to find out the unit of delta x, we have to separate the unit of the other two terms, but you never subtract them, okay? So when you have units of xf minus x naught, what do? You take into, you write down the unit of, let's see here, the unit of xf, okay? And don't subtract them, right? And the unit of, what's that? Okay, right in here. And the unit of x naught. Okay, the unit of xf is going to be the meter. And the unit of x naught is going to be the meter too, but you never sum that, you cannot sum that and put 2m. Okay, there is no such a thing as two meters as being the unit. You always display that as m, as the unit alone, okay? That's how you do. And let's see here, I don't like this square bracket. The way it is now is a nicer square bracket. Good. Like that. Still decrease. Okay. Okay, there's nothing much I can do. The square bracket of the second one is smaller than the first one. That's why. But that's not something I can do much about. Here you go. Okay, dimensional analysis. Now, what about for the velocity? Here you go. We do something similar. For the velocity or speed, right? Here you go. We put the v in the square parentheses to denote the unit of that quantity. We do the same for delta x over delta t. Right in here. We can separate the unit of delta x over the unit of delta t. Let's see. Unit of delta x over the unit of delta t. That's the distributive property that we are using here. Okay, and we do know that the unit of delta x is going to be the meter. It's so frustrating. My mouse is okay, and the unit of delta t is going to be the second. So here you go. That's what we are doing is called dimensional analysis. We are analyzing the unit, the dimension of a given quantity. Okay, and we can do the same for the s, right? We can do the same for the speed. Here you go. The speed here. Here is going to be d, right? Here is going to be d, and delta t is going to be the unit of this is meters, the unit of delta t is s. That's all that is to dimensional analysis. Dimensional analysis are usually important. Dimensional analysis can be used. What's the practical application of dimensional analysis? Okay, can be used in the following cases. In the following cases: 1, to determine the unit of a given quantity, and 2, to determine whether you are, to help you determine, not to determine, but to help you determine whether your solution, whether the solution of your problem is correct or not. Okay? Example, right? Suppose that you are calculating the velocity of a given object. You already know from the previous dimensional velocity that dimensional analysis, right? From the previous dimensional analysis, that the velocity has a unit given by meters per second. Okay? During the process of calculation, during the process of solving your problem, you obtain a given equation, and when you do dimensional analysis of your final equation, you find that the unit you obtain is not matching the unit of meters per second. What does it tell you? This tells you that you did some mistake. Either some mistake in the determination, in the derivation of your final equation, okay? That's one possible practical application of dimensional analysis. I usually do something like that whenever I'm dealing with very long problems, very big problems that involve very complicated formulas. If I'm not sure whether my final equation that I derived is correct, I do a dimensional analysis and see whether the dimensional analysis matches the dimension that I expect to obtain. Okay, it doesn't give you 100% assurance whether your problem is correct or not, but at least give you some certain sense of security that at least the dimension of your final equation that you derived has the proper unit. Okay, this dimensional analysis does not provide with 100% certainty that your equation is correct or not. However, it gives you some sense of security that at least the unit is correct. The unit is correct, okay? That was one of the applications for dimensional analysis. Okay. when doing dimensional analysis, keep the following in mind. One, you may multiply or divide different units. Okay? You may multiply or divide units different and alike units. You may multiply or divide different and alike units. What do I mean about that? Okay. Example. You may multiply meter versus meter, which results in meter square, which is the unit for area. Okay? You can do that, yes, you can do that. Meter versus meter. You may divide two. Let's see, example. Let's put like that. Second example. You may multiply, right here is multiply. I'm gonna put a space between those two. You may divide, you may multiply like units. Like units, okay? Example. I want to put this example right here at the top. Examples. You may multiply like units. This is the unit of area. I'm going to put that this is the unit of area, right? You may multiply different units, okay? Like, like for instance, kilogram times meter per second. You can do that. Yeah, you can do that. You may multiply or divide like units. Okay. Here's the case of multiplication of like unit, but you can also have, division. Let's put different lines here. You may multiply like units. You may divide like units, like in meter divided by meter, okay? When you divide one unit by the same unit, you always obtain the number one, okay? This is a unitless unit. This is a unitless unit. You may multiply different units, okay? Like kilograms times meters per second. This is the unit for linear momentum, which we're going to see later on. We will see later on. You may also divide different units like we did before, like meter per second, right? The unit for velocity or speed. Okay. However, you may not sum or multiply different units, okay? Just like in the case of the displacement. You may not sum or subtract different units. Okay, subtract. It's not allowed. For instance, it is not allowed, to sum meter with seconds. Okay? Not allowed. You're not allowed to subtract meter from second either. However, you allow it. However, if you are summing or subtracting units that are exactly the same one, like m plus m, you do not write down as 2m, you write that down as m, okay? The subtraction or summation of two like units will always going to be that unit without a number here in front of, okay? Correct way, the correct way. Okay, similarly, seconds minus seconds is still gonna be in seconds. Okay, still gonna be seconds. Correct unit. Kilogram, same thing. Kilogram minus kilogram. The result is going to be still the kilogram. Correct final unit. Okay. Those are the rules for dimensional analysis. You do not subtract one unit for the other. It's not going to be equal to 0. It's going to be equal to the unit itself. Just like I mentioned before. What else? And meters per second. Yeah, I did meters per second here, right? Meter square, kilogram. Okay, here we go. Meters per second. Let's see if I can organize better. You may multiply or divide different and unlike units. Example. Meter is meter, meter square. Meter divided by meter is going to be 1 because the meter cancel out with the meter. The meter downstairs cancel out with the meter. It's just like regular algebra. This is a unitless unit. You may also divide different units, meters per second, the unit of velocity or speed. However, when it comes to summation or subtraction of different units, you cannot do that. It's not allowed. However, you may not sum or subtract different units. For instance, meters per second is not allowed. Meters minus second is not allowed. Meter plus meter, yet is allowed. But remember, you are not summing meter plus meter equal to 2 meters. No, no, no. You have to have just to repeat the unit that you saw before. Okay, here is the same thing. Second plus minus second is not 0 seconds. It's not 0. It's the unit that you are handling. Kilogram minus kilogram, and so on. Okay. Example of compounded units in this. Let me give you some examples of compounded units. Other examples of compounded units, right? Area, I mentioned that at the top, right? Is the meter square. All you have to do in this case, in those cases here, all you have to do in the above cases is to do regular algebra with the units, right? When it comes to multiplication or division, in other words, when it comes to multiplication and division, all you have to do is to perform, regular algebra with the units. However, the same does not apply for subtraction and for summation and subtraction. However, the same does not apply for summation and subtraction. Okay? For instance, you cannot sum or subtract units that are different. If you're getting, what does it mean? What does it mean, okay? What does it mean? Well, it means that if you derived an equation that's summing two different terms, right? Two terms with different units, it means that you made a mistake in your derivation. Okay? I'm gonna put that after the other one as well. Okay? So here you go. What does it mean? What does the above mean? Does the above mean? Well, if you derive an equation that ends up summing two terms with different units, it means that you made a mistake in your derivation. Okay? But you can sum and subtract units that are the same. But again, you do not write that down 2 meters here. No, you don't write that. You repeat the unit itself. Okay? You get the same. Here you go. Let me do another example here. 1, 2, 3. An example of compounded units, right? Meters per second plus meters per second. You still get meters per second. That's the correct unit. Okay. So here are some examples of different units. Area is meters squared, speed is meters per second, volume is cubic meter, meter times meter times meter. Acceleration, we are going to see acceleration is going to be meters per second square. Force, the unit of force is the kilogram meters per second square. And this compounded unit shows up so frequently in physics that we give it a name, we call it the Newton. Okay? This unit of force is determined from one of the laws of physics, which we are going to cover soon. Okay. What else you have to know? Some of the things you may have already seen, I guess, right? There are other ways of expressing our measurements in the, right? Here you go. There are other ways of expressing our measurements in terms of a unit prefix. Have you ever heard of the prefix? In terms of a unit prefix. For example, 1 meter can be written down in terms of 100 centimeters. Okay, which is also given by 1,000 millimeters. What do we have here? What do we have? We have a unit that was written. We have 1 meter that was written in terms of another unit. But we must have a multiplicative factor here, okay? And where does the multiplicative factor comes from? Well, it's the prefix, it's the centi prefix, okay? The centi prefix, what does it mean? You have already seen that, right? Most likely. The centi means that 1 centi means 10 to minus 2, okay? So, superscript. I'm going to put a multiplication sign here, okay? 10 to minus 2. That's what centi means. And milli is something similar, okay? Here you go. When you multiply 10 to minus 2 is 1 divided by 100, right? Is 1 divided by 100. So here you go. Multiplied by 1 divided by 100. So when we do this math, we get back to our original result. The 100 cancel out the 100. I'm going to boldface it, and we return to the same result that is 1 meter. Okay? Another example. Here you go. 1 meter is also equal to 1,000 millimeters, right? What milli means, right? Milli means 1 over 1,000, 1,000. That's what milli means. And when you do the math, let me put the multiplication here. Milli is, I'm going to skipping, here you go. Let me write down the different way, right? Just like I wrote in the other way there. Milli, this prefix that you see right in here. Oh, I don't want Copilot. Yeah, here you go. I'm gonna boldface it. Here you go. Boldface it. This M doesn't mean meter. This M means milli. Okay? And milli means what? 10 to minus 3. Those are the most important ones that you're going to see. Okay? And 10 to minus 3 is what? 1 divided by 1,000. 1/1000, which return us to the original equation, that is 1 meter, okay? So you can come up with a table of different prefixes. Here we go. I'm going to write that down here. It's not all the prefixes that you're going to see out there, but it's enough. Let's see. Giga, and here is 1 tera. Oh, I put 10 to the 6. It's not 10 to the 6. It's 10 to the 12, okay? Tera is 10 to the 12. Giga is 10 to the 9, just like in gigabytes. 1 billion of a byte. 1 megabyte is 1 million, 10 to the 6. You have to memorize that, okay? Kilo is 1,000, right? Centi, just like we saw before, 10 to minus 2. Milli, 10 to minus 3. The ones that we are going to use the most frequently is going to be those 3. But the other 2 are also important, okay? We have micro. The symbol is the mu Greek letter. The Greek letter, that's 1 divided by 1 million, or 10 to minus 6. Nano and pico. You can find anywhere in the internet, okay? Unit prefix. Let's take a look at the internet so you know where to look for it. Unit prefixes in physics. Let's see, unit prefix table. Okay, here you go. There is the deci too, okay? I didn't list the deci there. Centi, the character is the C. See the milli? The milli, we use the letter M. Do not mistake this M by meter. Micro is the Greek letter mu. They put the Latin letter U, okay? Nano is lowercase n, pico lowercase p, and then you have the other ones that less frequently used, the femto, the atto, the zepto, the iocto, and the deca, 10 times, hecto, 100 times, kilo, 1,000 times, mega, a million, a billion, a trillion, and so on, okay? Peta, hexa, zeta, iota. The ones that are, like I said, I'm going to repeat here, the one that I'm going to use the most is going to be the centi, the milli, and the kilo. Those you must have memorized. The rest, you can consult at the table. Okay, eventually when you use those a bunch of times, you end up memorizing them. 11:48. Let me get some water here. Any questions? I'll give you some. Most likely you already have seen that before, right? But it's always good to review them. And now, there is some important, once you know those things about prefix of the units, you can start converting your units in one type from one unit to another one. Okay? For instance, how do you rewrite 1 square meter in terms of square centimeter? It's not straightforward. Those are the interesting things that we see in physics, right? There are certain problems in physics that doesn't seem to be common sense. You have to do the work, okay? So 1 square meter, how do you express 1 square meter in square centimeter? Do you write 100 centimeters square, right? That's the question that I'm gonna ask. Is 1 square meter equal to 100 square centimeter? 1 square meter equal to 100 square centimeter. That's the temptation that we have. Actually not. Okay? You must do the math, okay? You must do the math. Actually not, you must do the math. And let's do the math. Let's do the math together. We're going to do the math using the definitions for the prefixes, the correct definitions for the prefix, okay? So 1 square meter, okay? And I want to write down this square meter in terms of centimeter square. How do you do that? You have to account for this square that you see right in here, okay? I'm gonna boldface the square, okay? Remember that what you have right in here can be rewritten in the following ways. Can be rewritten with the meter inside the parentheses, right? With the square outside the parentheses. And now you can make the conversion from meter to centimeter. Okay, now you can make the conversion from, you know that 1 meter is 100 centimeters. See that? Now, do you see what's happening here? The 100 square ends up squared as well. So 1 square meter is not 100 square centimeters, it's more. It's more than that. Okay, so here we go. And then we go ahead. You expand that the terms in the parentheses, right? And then we end up getting 100 squared times square centimeter. 100 squared is going to be what? 10 to the fourth. 10 to the fourth. Or 10 to the fourth is what? Let's count the zeros here, right? 1, 2, 3, 4. 100 times 100 is 10,000 square centimeters. Like that. Okay. And you get something like that too for cubic meter, right? Cubic meter, for instance. What about 1 cubic centimeter? How to express 1 cubic centimeter in terms of meters? We do the same treatment. We start with 1 cubic centimeter, right in here. Go. right? We here write our cubic centimeter in terms of a parenthesis. And inside the parenthesis, we write down the centimeter in meter. 1 centimeter is 10 to minus 2 meters. And let's not forget this cubic here. And look what we get. We get 10 to minus 2 raised to the cube. No, you gotta raise to the cube. Yeah. And we have our centimeter, our meter, that's also raised to the cube. I'm going to repeat the one here, although it's not necessary. It's not necessary to repeat the one here, right? See this one here? No need to repeat it. And then we finish our calculation. 10 to minus 1 raised to the cube is 10 to minus 6. We have our meter, that's cubic, and 1 divided by 1 million. Okay, 1 divided by 1 million. That's what 1 cubic meter is in terms of a cubic. 1 cubic centimeter is in terms of a cubic meter. It's going to be 0.12345 right? 1, 2, 3, 4, 5, 6. Yeah. That's what 1 cubic centimeter is all about. And by the way, 1 cubic centimeter is also equal to 1 milliliter. 1 milliliter, right? Which is another unit of volume. Okay, and then you can practice it there at home. I'm gonna give you an assortment of simple exercises, okay? Problems to solve, problems for you to solve on your own. How to convert square meter to square feet, and vice versa. Don't forget you have to know the relationship between meter and the foot. How to convert square meter into square inch, and vice versa. How to convert 1 kilometer per hour into meters per second, and vice versa. 1 mile per hour into meters per second, and vice versa. Those are all sorts of different conversions that you must know how to do. Okay. So what we have done so far, one, we did building blocks of physics. Building blocks of physics. That's the first thing with summary so far, right? Summary so far. Building blocks of physics. What we did next. Let's go back here. Building blocks of physics. Go. We talked about the vector and scalars and scalar quantities. Just a brief introduction, okay? Brief introduction. We are going to see that brief introduction. Later on, we will look into more detail into that. We'll look in. We will have a more detailed look at vectors later on. So yeah, So we talked a little bit about vectors. What else did we do? We talked about units. Units, right? We talked about dimensional. Talked about dimensional analysis. We talked about the what else? We had something else. Let's see here. Oh yeah, introduced the following secondary definitions. Okay. What we introduced? Displacement, distance traveled, average velocity, average speed. Right? We introduce all those. I can even put them in a list format. Here you go. Displacement. 2. Distance traveled. 3. Average velocity. 4. Average speed. What else? We talk about the prefixes. Unit prefixes. Unit prefixes and how to convert them, right? And how to convert between them. That's what we have seen so far. 12 o'clock. Let's see. I think we can have a little break now. Let's see. Yeah, let's have a break. Let's have another break. And then we go, when we come back, we finish at 12:50, okay? Let us have another break. From 12:01 p.m. to 12:16 p.m. Okay, do I have any questions from you before we go into the break? Okay, so I see you in 15 minutes. Just a reminder for the lab. A reminder for the Wednesday lab. Yeah, you will need access to Microsoft Excel. No need for Microsoft Word, okay? In case you do not have, the college provides a license for this software. So you can check how you, in case you don't have Microsoft Excel, you can check there in the college site. Okay, you need access to the software because we'll be plotting graphs with it. One more student. Okay. Reminder for the Wednesday lab. Okay. So, and during the lab, I'm going to show you during the lab. I'm going to show you in case you have never, in case you never used Excel, comma, I will show you step by step how to include, in case you never plotted graphs in Excel. I'll show you step by step how to do that. How to do that. Wednesday. Okay, so we started doing that one-dimensional motion. Now we are going to elaborate on that. Here you go, one-dimensional motion. The way I'm doing is slightly different from the book. The way I'm doing one-dimensional motion is slightly different from the book. The way I'm doing one D motion is slightly different from the book. The book starts with vectorial notation right from the bat. I think it's too much. I think it is better to introduce you to one-dimensional motion, to 1D motion first, and then expand to 2D motion. 1D motion using, here you go, first, 1D motion first using regular scalar notation. Okay. The book starts using vectorial notation right from the bat. I think it's better to introduce you to 1D motion first using regular scalar notation, and then cover vectors, and only then expand the concepts of 1D motion to 2D motion. So you're going to see that the book, just wanna cram the 2D motion right away from the beginning. Okay, so we're going to do it slightly different. I think it's better the way I do. And I already started covering, I already started covering some of the concepts of 1D motion. Okay, right, I start doing that, but now we are going to go deeper into that. Let's see, 6 digits. Someone left me a message here. Can you please send me the Wiley Plus registration code? Okay, the Wiley Plus registration code is in the syllabus, is it? And it is also, let me see if I have it here. No, it's let me get that. Let me get you the 6-digit code. Okay, so if you look into the syllabus, okay, the 6-digit code is right here. I'm sending that to you anyway. Let me send to everybody in case someone else. This is the 6-digit Wiley plus registration code. Okay. And if you go in Canvas, there is also the flyer that I posted there with the registration code. And not just the registration code, but also the instructions. Okay, good. Right in here, this flyer here. Okay. So you have 2 places to look for it. Okay. And here, B00230. Okay. So close it and close it. So already start covering some of the concepts of 1D motion. Well, in order to cover the 1D motion, we have to refer to one of the basic definitions that I introduced before. Remember? The primary definition of the position as a unit of length. And then I introduce you to the idea of displacement. That's the secondary definition. Okay, and what else you have to know? You know, x final minus x initial, okay? So we, in physics, we try to simplify the notation as much as you can. And that's exactly what I did here in the next step, okay? So let's put that centralize. Note that I use xf as the notation, but we in physics and math, we try to simplify the notation as much as we can. And so what's the simplification that we made? The simplification that we made is that we dropped this xf subscript here, okay? So instead of writing down the final position as being xf, now we are writing down the final position as being x alone. X would be the generic position, the generic final position, okay? That's what we did here. And xf is equal to x. And here is the example that we did before. The object going from 5 meters, position of 5 meters, which was the initial position, to the final position of 3 meters. Okay. I told you about the distance traveled. And again, I'm just repeating what I did before here for completeness sake. My computer is slow. Yeah, something happening here with my computer that it is, for some reason, it is thinking. I do not know why. Maybe I have too many stuff open here. Let me start closing some of the screens. This one, I will close this one as well. Yeah. Oh, that's frustrating, isn't that? Must be something in Microsoft Word. Word not responding. Let's see, let me quit Word altogether. Should be quicker. Let's see. Okay, good. It fixed. That's great. It's fixed by itself. Okay, so just for completeness, I'm going to repeat what I did before, right? In addition to the concept of displacement, we also have the concept, the idea of distance traveled, D. Whatever is shown in the odometer of your car is not the position nor the displacement, but the distance traveled by your car since it came from the factory. Okay? Distance travel in this case for one-dimensional motion, for the case of 1D motion, comma, the distance traveled is given by the following formula. And I can center justify 2 meters, right? Without the minus sign. I'm going to emphasize here that we have a plus sign here for the distance method, distance covered. Keep in mind the above equation applies only to 1D motion. If we introduce a second dimension, then the distance traveled will be, maybe, right? Maybe, I'm going to put it, maybe a far more complicated formula. Okay? And there's a reason for that. But for now, since we're dealing with one-dimensional motion only, we can write down that the distance traveled is going to be the modulus of the displacement. Okay? Revising what we did before, I use the notation for average velocity, right? Just as a V. Let's but there's a better notation for the average velocity, and I want to correct that. Here we go. We need to put a subscript AV there. Average velocity. Don't forget it's average velocity vector. Let's see if we have another one here. Nope. I want to correct that. Instead of just V, let's use the AVG, right? That would be the symbol for average velocity, but there's another symbol for average velocity too. Let's see, this one here. Oftentimes we also, any average quantity, we can either denote by a subscript AVG downstairs or this bar at the top. Any average quantity. If you prefer to use this one, that's fine. If you prefer to use the other one, it's fine as well, okay? And the scalar counterpart of the average velocity is the average speed. I'm just fixing what was missing before, and I'll put S right here. And I will take this one out of here and place it here. And like I said before, you can also use the bar symbol to denote average of a given quantity. Okay, well, let's see if there's more. Average velocity, here you go. AVG. Average speed, I'm going to put it AVG. Any more? Oh, that is here. average AVG and AVG. I think we covered everything, everyone, right? And the average velocity is a tertiary definition. It's not even secondary, it's a tertiary. Primary starts with the position, secondary is going to be the displacement, and then the average velocity is a tertiary definition. And you can keep on going on and on, right? Quaternary, and so on. Primary, secondary, tertiary, quaternary, and so on. Okay. And just like I said before, you can never sum or subtract quantities, definitions or quantities that have different units. Okay, can have sum or subtract. Subtract quantities and definitions that have different units. For instance, you cannot sum position with time. You cannot subtract position with time. Not allowed. Not allowed mathematically, right? It's just like summing bananas with potatoes. And similarly, if you cannot subtract, you cannot sum either. Because you cannot do that because they have different units. By the same token that we cannot sum different units, we cannot sum quantities or definitions and definitions that have different units. You cannot sum average velocity with position. You know, here you go. You cannot do that. Average velocity with position because they have different units. However, you can multiply and divide quantities and definitions. However, you can multiply and divide quantities and definitions that have different units. And going back to the progression of terms, right? To the progression of the definitions, to the progression of the quantities. We have the position, we have the displacement, and the displacement is at the same level as the distance traveled, okay? We have the average velocity and we have the average speed here. That's the definition of average speed. And we did the examples that right in here, and here you go. And now what we're going to do? We are going to (12:40) already, right? Let's see if we have time to do that. Okay. Yeah, so in addition to this average velocity and average speed, we also have, in addition to the average velocity and speed, we also have something else that we call the instantaneous velocity slash speed, okay? So here you go. Position, I'm not writing down the distance traveled, okay? displacement, let's put here, displacement and distance traveled. Let's put this way, distance traveled, average velocity and average speed, and average speed and instantaneous velocity and instantaneous speed. Okay, and that would be quaternary, right? Quaternary. So let's look how we can define instantaneous velocity, instantaneous speed. Okay, instantaneous velocity is the value of the velocity that you take at a specific instantaneous time. And mathematically speaking, here you go, instantaneous velocity, the value of the average velocity taking whenever the delta t is very small or very close to zero. Okay? Notice that as delta t becomes very small, so there's delta x. Can you picture that in your mind? As the amount of time becomes shorter and shorter, of course, the displacement is going to be smaller and smaller as well. This applies both for velocity and for speed. It's like dividing a very small number by another very small number. And when you do that, comma, the result is not going to be necessarily zero or infinite or infinite. Instead, it may be a finite number. Let me emphasize here. Do you know any example in which you divide right? Do you know any example in which when you divide a very, let's say, when you divide 0 by 0, right? And you still get a finite number, huh? Do you know any example like that? When you divide 0 by 0 and you still get a finite number? We have plenty of examples in math in which something like that happens. Okay? There is this function, for instance, called sine of x divided by x. You know? For instance, one example. Calculate sine of x divided by x. The value of sine of x divided by x whenever x approaches 0. Okay? Or whenever x is equal to 0. X is equal to 0. We do not know how to divide this number. Mathematically speaking, we cannot divide this number, but we can do something similar. Okay? It is not possible to divide 0 by 0, but it is possible to do something else that is similar to that. Okay? So instead of dividing 0 by 0, think about that, right? When you make x equal to 0 here, sine of 0 is going to be 0, right? So you have 0 by 0. Similar to that. And what would be similar to that? Okay, we do something else that we do a limiting operation, okay? And by limiting operation, it's something like that. Here you go. We even write that down. Limit as x goes to 0 of sine of x divided by x. We have 6 more minutes to go. I think we can do what I want to do. And it is possible to do that. It is possible to do this operation manually. Okay? You start, for instance, you start with x equal to 1, substitute in the above equation, substitute in the above equation, comma, get a result, and repeat for x equal to half, right? Then for x equal to 0.25, okay? And so on. Think about doing that manually. As you keep on getting your results, you will learn that this ratio approaches a finite value, okay? And if you have seen that before, you should know that this ratio should be equal. I'm not going to tell you yet, but think about that. What number do you think you're going to get if you do this operation, right? We can do this operation, by the way, with Excel. It's possible to do this operation manually. However, I don't recommend because it's too much work. Okay? Let's put it this way. However, I don't recommend it because it is too much work. There's a better way of doing this operation, right? So what would be the manual procedure, right? You start with x equal to 1, substitute in that equation, and then you're going to get a result. It's possible to do that. Then you get another number, less than 1, 0.5. You're going to approach 0 little by little. Substitute sine of 0.5 divided by 0.5, and you're going to get a certain result. Then you get a smaller value for x, 0.25, and so on. You keep on repeating several times. When you repeat it several times, you are going to see that you are going to get into, you're going to see that this ratio is going to converge to a finite value. And I'm going to do that with you right now. Let me get that here, Excel. We can do that with Excel in a very quick way. 12:47, I have 3 more minutes. Let's see if I can do that in less than 3 minutes, okay? Let's see, here you go. I'm gonna come up with my spreadsheet here. Okay, I'm gonna get the values of x here in this column, the values of sine of x in the other column, and then I will calculate sine of x divided by x using that limiting approach. I can start from whatever number I want. I choose to start, for instance, at 1, okay? And then little by little, let's see, little by little, I will half it, right? I will take the half of that. 1/2, 0.25, 0.12, whatever, right? See what I'm getting here? These numbers are getting closer and closer to 0. See that? These numbers are getting closer and closer to 0. And now I repeat, let's stop here at 6.1 times 10 to minus 5, right? Here is 1, 2, 3, 4. That's 10 to minus 4 here. 1.22 times 10 to minus 4. So when you divide by 2, you're going to get a number that's 10 to minus 5. Let's see if we can go further than that. Let's see. Yeah. See, it's going closer and closer to 0. And then what do you do next? You calculate the sine of 1, right? And the sine of half, and the sine of 0.25. Don't forget that what we're getting here is 1 radian. It's not 1 degree, okay? Half radian, 0.25 gradients, 0.125 radians, okay? And so on. And look what we get. The sign gets closer and closer to 0 as well. Okay? And now we do the ratio. Let's see what happens when we do the ratio. 12:49. 1 more minute to go. Okay? So I'm dividing sine of x by x. Remember, I told you I don't recommend you to do it manually, not even with your calculator, okay? Because it's too much work. But we can do that very quickly with Excel. Here you go. As I divide the sine of x by x, look what happened to those numbers. It was initially 0.84, then it becomes 0.95, becomes 0.98, 0.99. Do you see the number that this ratio is converging towards? 0.99. Look, this number is getting closer and closer to 1. Do you see that? That's what's happening. Eventually, when x goes to 0, you do get a value of 1. You do get a value of 1. And that you can do using Excel, okay? Excel or even differential calculus, right? Differential calculus technique, okay? And that, why am I doing that? Okay, this is an example in which 0 divided by 0 converges towards a finite number, okay? Just like we are doing for the instantaneous, just like we are going to do for the instantaneous velocity, okay? So 12:51, we can stop now. Do you have any questions? I have a office hours right now. And if you want to hang around after the class, I'll be available. And we'll also post those notes there in Canvas. Okay? So see you on Wednesday for the lab.
Professor, I have a question.
Yeah, let me stop here recording first.